All right, welcome chemists to chapter 14, lecture number 2 from Ralston Valley High School Chemistry's AP lecture series. In this lecture, we're going to be discussing calculations of pH values for both strong and weak acid and base calculations. Let's get started. All right, much of what we're going to see here at the start of the lecture is going to be a review from last year's work in the acid-base unit in your regular chemistry class. We're going to start off here today with a discussion of the pH and pOH scales. As you recall from last year, chemists use a p function to represent the negative logarithm of a numeric value. And a logarithmic scale is very useful when you're dealing with values which might vary by many, many orders of magnitude, such as the hydrogen ion concentration in solution. So by definition, the pH of a solution is the negative log base 10 of the concentration of hydrogen ion in solution, whereas the pOH would be the negative log base 10 of the hydroxide ion concentration. This year in AP Chemistry, we'll also be dealing with a couple other values here. Again, you might see in the course of your reading the book a value of pKa, which represents the negative log base 10 of the Ka value, that is the acid ionization equilibrium constant, or a pKb, which would be the negative log base 10 of the base ionization constant Kb. Now, understanding from our previous discussions that the concentrations of hydrogen ion and hydroxide ion are inversely proportional to each other within the aqueous solution, and they're related to each other by that value of Kw, we can look up here at the scale that we have posted for you on the right side of your page there, which is going to look at the relative concentrations of hydrogen and hydroxide in solution. So you'll see on our number line scale here that we have the hydrogen ion concentration range between around a molarity of about 1 molar on the high end down to a molarity on the low end of around 10 to the negative 14th molar. Now it might seem odd that we're kind of cutting off that hydrogen ion concentration at that upper range of around 1 molar, but recall for a strong acid that undergoes complete dissociation, as that acid dissociates into its component ions and the concentration of those ions become greater, the process of ion pairing will cause those ions to reform back into the molecular acid, and that process is going to be more favorable in the reverse direction at higher concentrations. So the big takeaway from this idea is that even though you might have an acid with a nominal concentration of greater than 1 molar, like let's say, for example, you have concentrated hydrochloric acid whose molarity is given around 12 molar, because of that process of ion pairing, the actual hydrogen ion concentration in solution will be significantly lower than the actual 12 molar value given as the nominal concentration of the acid. That is to say, even strong species stop acting quite so strong when they get highly concentrated. And as such, we generally say that the highest meaningfully measurable concentration of hydrogen ions within solution is somewhere right around a concentration of 1 molar. So with that being said, at a concentration of hydrogen ion of 1 molar, if we take the negative log of that value, we'll find a pH value of 0 for that particular solution. And in this theoretical solution with a hydrogen ion concentration of 1 molar, we could also calculate the concentration of hydroxide ion by using the relationship described in the autoionization constant Kw for water. Because the product of hydrogen ions concentration times the hydroxide concentration always yields the value of Kw, that is 1.0 times 10 to the negative 14th. In a 1 molar hydrogen ion solution, we would therefore expect to see a hydroxide concentration of 10 to the negative 14th molar. And then taking the negative log of that value to find then the pOH, we would find a corresponding pOH of 14 in that solution. Now we could go through the same thought process here as we look at a solution in which the hydrogen ion concentration was as low as it possibly could be within solution. That is to say, within a solution whose hydroxide concentration was 1 molar, we would expect to see a hydrogen ion concentration of 10 to the negative 14th molar. And therefore, we would get corresponding pH and pOH values in this solution of a pOH of 0 and a pH of 14. Now, if instead of measuring the pH of a solution, we were instead to measure the pH of a sample of pure water, the concentrations of hydrogen ion and hydroxide ion, recall, are not 0, but instead are each 1.0 times 10 to the negative 7th molar at 25 degrees Celsius due to the autoionization process of water. And as such, in a pure water solution, we would expect to find both a pH and a pOH of being the negative log of 1.0 times 10 to the negative 7th, which is a pH or pOH of 7, respectively. And something we want you to notice here is that while the solution's composition is going to be changing depending upon the concentrations of hydrogen and a hydroxide ion, the sum of the pH and the pOH values always sums up to a total of 14. So in summary, whereas the product of the concentration of hydrogen ion times hydroxide ion always equals the value of Kw, that is 1.0 times 10 to the negative 14th, the sum of the pH plus the pOH always equals a sum of 14. All right, now that we have revisited how to calculate a pH, we're now going to take a look at the pH square. The pH square is a quick tool that we use in order to make calculations between the relative concentrations of the ions, the H positive hydrogen ion and the OH negative hydroxide ion, and then the pH and pOH values of a particular solution. If you remember back to your first year chemistry, this is kind of a guide map similar in vein to the mole map which many of you have used in the past. So let's take a look at the relationships that exist between these to kind of develop a pathway between each of these different calculations. Starting off with the relationship between the hydrogen ions concentration and the hydroxide ions concentration. Recall that the relationship between these two concentrations is an inverse relationship. That is, if hydrogen ion concentration goes up, the hydroxide concentration in the solution correspondingly goes down. And that relationship is defined by the value of the auto-ionization constant Kw for water. So if you want to move between these two concentrations, all you have to do is to manipulate the equation. Kw equals concentration of H positive times concentration of OH negative. From there, if we want to move from one of the concentrations to one of the P functions, recall all we need to do is to take advantage of the definition of the P function, which is again a negative logarithmic function. So to move from the concentration of hydrogen ion to the pH of the solution, all we have to do is to take the negative log of that concentration of hydrogen ion within the solution. Or correspondingly, if we want to move between the concentration of hydroxide ion and the pOH of the solution, all I would have to do there is to take the negative log of the concentration of hydroxide ion. Now, in order to move in the reverse direction, that is to go from a P function back into one of the corresponding concentrations, I would have to inverse the operation of the log function, which is, as you are familiar, an exponent. So therefore, if I want to move from pH to the hydrogen ion concentration, all I will need to do is to take 10 to the minus pH power. And again, it's going to be the minus pH power, recognizing that the P function is the negative logarithm. And as well, we could find the hydroxide ion concentration by simply inversing the operation again. That is, the hydroxide concentration is 10 to the minus pOH power. So we're now able to move around most of the pH square. The only thing that remains now is the relationship between those two values at the bottom, that is between the two P functions. And as you recall, as we derived on our previous slide, the sum of the pH plus the pOH for any given solution always equals 14. So if you know one, the other simply would be 14 minus the corresponding pH or pOH. All right, so we now have developed relationships between all of these different corners of our pH square. Let's now do a real quick, just easy example, moving around the square to see how this would function. Imagine for a quick moment here that we have a hydrogen ion concentration in our solution of 1.0 times 10 to the negative third molar. If I wanted to go from that hydrogen ion concentration to a pH, I would simply take the negative log base 10 of that value, 1.0 times 10 to the negative third, which gives me a pH of 3.00. Remembering that we would have 2 decimal places after the 3 right there, because looking at our significant figures rules, the 3 is actually coming from the exponent power of our concentration and therefore does not count as one of the significant figures in our pH. So 3.00 with the 2 zeros being the significant figures after the decimal place for that pH. Now to find my pOH, I recognize that the sum of pH plus pOH always equals 14. And as such, the pOH of my solution would be equal to 14 minus my pH of 3, which would give me a pOH of 11.00. And now that I've got the pOH, I want to move back now into a concentration of hydrogen ion. Now I'm going to be using the inverse operation of that P function, which again is the exponent power. So my concentration of hydroxide ion in a pOH 11 solution would therefore be 1.0 times 10 to the minus pOH, which is 1.0 times 10 to the negative 11th molar hydroxide ion. And I can double check my work now by looking at the relationship between those two upper places on my pH square. That is the product of my hydrogen ion concentration times my hydroxide concentration should equal the value of Kw. And indeed it does, as we see, the hydrogen ion concentration of 10 to the negative 3rd times the hydroxide concentration of 10 to the negative 11th yields the value of Kw, that is 1.0 times 10 to the negative 14th. All right, so we can now easily manipulate the pH square, and we can see that if you can calculate one of those 4 variables there, it's very, very easy to move your way around to find all of the others, whichever you need. We'll move on to our next slide. All right, moving on, we're going to go ahead and take a look at an example problem here in which we're going to ask you to calculate the pH of a solution containing a strong acid or a base. Now, importantly here, folks, the way you calculate pH is going to be very, very different if you are using a strong species like hydrochloric acid or sodium hydroxide versus a weak species like acetic acid or ammonia. The reason why being that strong species, as they dissolve in solution, undergo complete ionization, and thus we are safe to assume that the given concentration of hydrogen ion in a strong acid solution is equivalent to the nominal concentration of the acid, as every one of those molecules of the acid will undergo complete dissociation into its component ions. And likewise for a strong base, the concentration of hydroxide ion would be equal to the nominal concentration of that strong base in solution for the same reason, that is, the dissociation is complete. That would not be the case for a solution involving a weak acid or base, in which the acid or base is only going to partly ionize in solution, and as such you're going to be required to deal with the calculations involving equilibrium chemistry, that is, setting up ice tables and so on. So we're going to start off by looking here at strong species only. The first thing I would recommend when you're dealing with any acid-base calculation in AP chemistry is to make sure you start by thinking about whether the species you're dealing with is strong or weak, and then you'll know the pathway you need to follow in order to get to your pH calculation. So having a look at our example here, we're going to be looking at example number 1, in which you're going to be asked to calculate the concentrations of hydrogen ion and hydroxide ion, as well as the pH and pOH of a solution, which is made by adding 10 milliliters of a concentrated solution of hydrochloric acid at 12 molar to enough distilled water to end up with a final volume of 500 milliliters of the solution. And as a starting point again, recognize the acid we are using there, hydrochloric acid, is one of our strong acids, and as such we are going to be safe to assume that that acid is going to undergo complete ionization as long as we are at low enough concentrations that ion pairing is not a problem. Now at first glance that might seem to be a bad assumption because a 12 molar concentration seems to be very, very highly concentrated acid. But recognizing what we're doing to this acid is by adding up to a bunch of water, we are going to be diluting that solution to a much, much lower concentration, and as such, it'll be safe to assume that the concentration of hydrogen ion in solution is going to be equivalent to the nominal concentration of that molecular acid in our calculation. So as a starting point, we'll go ahead and recognize that with a dilution, we want to use our dilution equation. That is M1V1 equals M2V2, where our initial molarity M1 is given as 12 molar. The initial volume of that solution is a 10.0 milliliter solution, and the final volume upon dilution, that is my V2, would be 500.0 milliliters. We'll rearrange our dilution equation, which gives me the new expression M2, the final molarity, is equal to M1 V1 over V2, and simply go ahead and plug in our given variables. That initial molarity M1 is 12 molar, our initial volume V1 is 10.0 milliliters, and our final volume of solution V2 is 500.0 milliliters. We'll see milliliters cancels out properly here in our calculation, yielding a final answer of a diluted concentration of 0.24 molar HCl for our calculation. So, that being said, that 0.24 molar HCl as a strong acid will undergo complete ionization into hydrogen ions and chloride ions, and as such, I can now state that the hydrogen ion concentration in my dilute solution is also therefore 0.24 molar. And at this point, with the hydrogen ion concentration, I'm simply into my pH square. I can now calculate my pH of solution by taking the negative log of that hydrogen ion concentration. So the negative log of 0.24 yields a pH of this solution of 0.62. Finding now my pOH, recognizing the sum of pH plus pOH always equals 14. My pOH would therefore be 14 minus my pH value of 0.62, giving me a pOH of 13.38. And I can now work my way backwards up to the concentration of hydroxide ion in solution by taking 10 to the minus pOH power, which gives me 10 to the minus 13.38, otherwise known as 4.2 times 10 to the negative 14th molar OH negative. And again, just to be tidy here, I can double check my work, recognizing that the product of my hydrogen ion concentration times my hydroxide concentration must always equal that value of Kw. You'll notice that the hydrogen ion concentration of 0.24 times my hydroxide concentration of 4.2 times 10 to the negative 14th yields that expected value of 1.0 times 10 to the negative 14th. All right, easy peasy. We've now calculated the concentrations of hydroxide, hydrogen ion, and the pH and pOH of a strong acid solution. Move on to our next slide. All right, another quick example here, this time involving a calculation of the same four variables, that is the concentrations of hydrogen ion, hydroxide ion, pH, and pOH, this time of a solution made not by dilution, but instead by dissolving a ionic solute, in this case 5 grams of sodium hydroxide, into enough distilled water to make a solution of final volume 2.00 liters. So again, the key to solving these problems, again, is to recognize first off what type of species we are dealing with. This is NaOH, that is one of our alkali metal hydroxides, and therefore a strong base. And as such, what I'm going to start with here is trying to find the concentration of hydroxide ion in my solution. So as a starting point, we want to go ahead and take a look at the definition of molarity in this calculation. That is, molarity by definition is the moles of solute per liter of solution. I don't have moles, instead I was given grams of my solute, which means first step is I need a quick grams to moles conversion. In order to do so, we will go ahead and set up a quick monorail. Monorail! With this value of 5.00 grams of NaOH as our starting point, we will now divide by the molar mass of 39.997 grams of sodium hydroxide per mole of sodium hydroxide, yielding an answer here of 0.125 moles of NaOH present in our solution. But again, I don't want the moles of NaOH, I want the molarity. And as such, I'm going to go ahead and take a look at the molarity definition, which is, again, moles per liter. We have 0.125 moles of our solute dissolved now in 2.00 liters of solution, yielding a molarity of 0.0625 molar NaOH. And as again, this is a strong base, I am safe to assume that that sodium hydroxide will undergo complete dissociation in solution, yielding therefore 0.0625 molar hydroxide ion concentration in the solution as well. And now that I've got a hydroxide concentration, all that remains now is to solve the rest of the pH square. I'm always going to go ahead and start by finding the P function here. In this case, the pOH of my solution would be the negative log of the hydroxide concentration. So the negative log of 0.0625 by my calculation comes out as a pOH of 1.204. Now quickly we can find our pH by taking 14 minus that pOH value. 14 minus 1.204 yields a pH of the solution of 12.796, a very high pH, which again should make logical sense given that this is a strong base that we are dealing with here. And then last but not least, to get back to my hydrogen ion concentration, I can take 10 to the minus pH power Plugging in my numbers there, 10 to the minus 12.796 yields a hydrogen ion concentration of 1.60 times 10 to the negative 13th molar H positive in my solution. All right, so in these last two examples, again, we've seen how quickly and easily we can calculate all of those variables involving the pH square for either a diluted acid solution or for a base that is dissolved into solution using the definition of molarity. All right, we'll move on to our next slide. Now that we have calculated the pH and POH of strong acid and base solutions in the last couple of examples, it's time to move on to a more complicated set of calculations now involving what to do if we have a weak acid or base solution. In order to deal with a weak acid or base solution, it's really very important that we focus not just on making algorithmic calculations, but instead focusing on the actual chemistry of the species in solution. That is, we have to stop and think before we just start randomly calculating things. So I've given you here a sequence of steps to go through in terms of correctly calculating the pH or POH of a solution involving a weak acid or a base. And note that it's a significantly more involved process than dealing with those strong species, which undergo their complete ionization in solution. So starting off, the first thing we always want to make sure we do is to recognize that we want to list the major species present in our solution in order to determine which of those species might end up producing hydrogen ions in solution itself. This can be a very simple process involving a weak acid or a base, but it also can be very complex because sometimes we have to take it into account the idea that water itself, the solvent in our reaction here, is going to also be a species which can generate hydrogen ions in solution. And depending upon the concentration and K values of the acids and bases involved, sometimes the contribution of water to the hydrogen or hydroxide ion concentrations in solution are not going to be negligible and therefore will need to be accounted for in terms of our calculations. This is also going to be a very important step in terms of dealing with solutions which involve mixtures of weak acids or base solutions. Once we have gone through and identified all the species that can produce hydrogen ions in solution, the next step is to figure out what the dominant source of hydrogen ions are in that solution by comparing the relative Ka values of the species present. What we're really looking for here is which species is producing the vast majority of the hydrogen ions in the solution. In general, one species should be producing orders of magnitude more hydrogen ion in the solution for the calculations we'll be dealing with, and as such, that's the one we really want to focus on. All the secondary contributors of hydrogen ion to the solution are essentially, for the most part, going to be minimally important in terms of determining the actual hydrogen ion concentration of the solution as a whole. So we're simply going to find the Ka values of each of the different species, and therefore we can determine which of them is the strongest acid and the species which is therefore most likely to be donating the majority of the hydrogen ions to our solution. Once we've identified that dominant source of hydrogen ion, the next step is to write the equilibrium expression for the dominant equilibrium. That is, we want to write the corresponding Ka expression that correlates to the dominant source of hydrogen ion within our solution. And then having written that equilibrium expression, we can go ahead and set up our ice table using our familiar methods. Once we've got that ice table set up, we'll follow the process we have done in the past. That is, we will substitute the equilibrium concentrations defined in terms of x from the ice table into the equilibrium expression, the Ka or Kb of the corresponding acid or base we're dealing with. And at that point, we'll use our assumption method in order to calculate the concentration of the dissociated ions in solution, according to the same methods we've shown you in our previous discussions of ice tables and equilibrium chemistry. Having then calculated the concentration of the pertinent ion, that is either the hydrogen ion or hydroxide ion in the solution using the ice table, at that point we can verify our assumption was a safe assumption to have made using our 5% rule, and go ahead then and use the calculation of pH as we've shown you previously in this lecture. So it's again a more involved sequence of steps here. I think the easiest approach to this is simply to start doing the problems and see how they work out so we can apply this in action. We'll move on to our next slide. All right, moving on now to an example here for the calculation of a pH of a weak acid solution. In example 3, we're going to be asking you to calculate the pH of a 0.50 molar solution of hydrofluoric acid, HF. The Ka value for this species is 7.2 times 10 to the negative 4. So we're going to kind of follow the sequence of steps outlined in the previous slide in order to come up with the final pH calculation. Starting off with the recognition that I want to understand the species in terms of the relative strength of this acid or base. HF is a binary acid, and it's not among the species listed as the strong acids, which implies, therefore, hydrofluoric acid is a weak acid, as evidenced by its small value of Ka. And as such, I'm going to follow, again, a weak acid pathway here for my calculation. The very first thing I want to do is I want to list the major species present in my solution. So obviously, if this is an aqueous solution, present in the solution as major species, we have water, number one, and then our species HF, the hydrofluoric acid. That hydrofluoric acid is going to be the major species rather than the hydrogen ion in solution because, again, its ionization is only going to be partial. A very small fraction of those HF molecules are going to dissociate into their component ions. So really we just have those two major species, water and hydrofluoric acid. I can write now a couple of equations for generating hydrogen ion in solution from those major species. Starting off, number one, I'm going to write hydrofluoric acid's dissociation here, showing it separating apart into the component ions of the hydrogen ion H1 positive and the fluoride anion F1 negative. And again, I'm going to write this as an equilibrium, as this equilibrium favors the left side of the reaction. That reverse process, again, is the favorable process for a weak acid. And the other species in solution, which might be able to end up generating hydrogen ions in solution, is water itself via the autoionization process. I'm going to write this as a hydrolysis reaction, showing water reacting to itself, donating a proton from one water molecule to another to form hydronium ions and hydroxide ions. And I recognize again at this point that that hydronium ion is really just synonymous with the hydrogen ion in my solution. The K value that governs this particular reaction here is that of Kw. That is a value of 1.0 times 10 to the negative 14th. Now, comparing the relative K values of each of these processes here, I see the Ka for hydrofluoric acid is many orders of magnitude larger than the Kw value for the autoionization of water. And as such, it's apparent from that hydrofluoric acid is a much stronger acid than water, and therefore HF will be my dominant source of hydrogen ion in my solution. So I'm going to focus my attention then on the HF, as this is the one which is going to be producing the vast majority of hydrogen ions present. So with that then, I'm going to go ahead and write the equilibrium expression for that dominant equilibrium, that is my Ka expression. The Ka for my reaction would be the concentration of products over reactants, which is, again, going to be concentration of H positive ion times F negative ion, all divided by the concentration of the molecular acid HF. And now I'm going to go ahead and set up an ice table using that dissociation equation for hydrofluoric acid as my guide. We'll plug in my values that I'm familiar with here. That is my initial concentration of the HF given to me in the problem was a concentration of 0.50 molar. And we're going to go ahead and assume initial concentrations of hydrogen ion and of fluoride ion of 0 in solution. From this initial starting point, I know my changes in concentration for HF must therefore be a minus X. And for the hydrogen ion and fluoride ion, those are both going to be plus X's. And that yields, therefore, equilibrium concentrations defined in terms of X as 0.50 minus X for HF, and then X for hydrogen ion and fluoride ion, respectively. All right, so at this point, if we look to our previous slide, the steps we've made through right now are we've set up our ice table. The next step, as you're familiar, is to go through and to substitute the equilibrium concentrations defined in terms of X from that ice table into my equilibrium expression, that is, into the Ka expression. So plugging in from that, I get my Ka value of 7.2 times 10 to the negative 4. That is now equal to the product of hydrogen ions concentration times fluoride's concentration, which at equilibrium are both X, so that numerator therefore is going to become X squared, divided by my concentration of fluoride ion, which is given to me here as 0.50 minus X. And looking at where we're at right now, I recognize that this is going to turn into kind of a nasty quadratic equation here. I don't want to deal with solving a quadratic formula, so I'm going to go ahead and use the assumption method in order to solve for X. recognizing that my value of Ka of 7.2 times 10 to the negative fourth is a very small value. A small Ka implies a small ratio of products over reactants, which itself implies a small numerator, which therefore implies the value of x is small. So I'm going to go ahead and assume that x is not just small, but specifically that x is very small compared to that initial molarity of 0.50 molar. And by making that assumption here, I will simplify down my expression now to the Ka value of 7.2 times 10 to the negative 4 is now equal to x squared divided by 0.50 minus x, which is a very small number, so 0.50 minus a very small number will simplify down to essentially pretty darn close to 0.50. And I can now solve algebraically from here. We will multiply both sides of our equation by 0.50, which means we can then cancel that out of the right side of my equation there. And then all I need to do then is take the square root of that value, and finding the square root of 7.2 times 10 to the negative 4 times 0.5 using my calculator comes out to be an x value here of 0.019 molar. And before I move on, recognizing that I do now have an x value and I used an assumption to get to that point, I want to make sure I prove that assumption to be valid. As such, I'm going to check the assumption by dividing my x value of 0.019 molar by the initial thing I assumed it was small in comparison to, which in that case was a molarity of 0.50 molar. And I'll multiply that by 100 to express this as a percentage. And we find here a percent error introduced by the assumption method here of 3.8%, which falls below the 5% reasonable assumption of error we make in these problems, and therefore this is a valid assumption for us to have made. So we now have a valid value of x, and I can recognize, looking back to my ICE table, that what really was important about solving for x there is that the value of x in this equation is the concentration of hydrogen ion at equilibrium. And as such, I can very easily now find the pH of my solution by taking the negative log of that concentration of hydrogen ion. That is the negative log base 10 of 0.019 molar, yields for me here a pH of 1.72. A logical answer, recognizing again that this is a fairly concentrated acidic solution. Now, note importantly here, folks, that that value of a pH of 1.72 is a higher pH than would have been found had this acid been a strong acid and undergone complete dissociation into ions, because at that point I would have ended up with a hydrogen ion concentration, had this been strong, of 0.5 molar, and the negative log of 0.5 is obviously a value which is less than 1. And when I calculate here in my calculator, that negative log of 0.5 comes out as a pH of 0.30. So again, a strong acid solution at that concentration would have the pH of 0.30, but my weak acid HF instead has a higher pH value of 1.72, a recognition of the fact that it dissociates to form fewer hydrogen ions in solution than if the acid were strong. All right, there is calculation of the pH of a weak acid solution. We'll continue and move on. All right, another pH calculation example problem here. This one is really illustrative of an important concept we discussed in the sequence of steps we described a couple of slides ago in order to find the pH of a solution. So we're going to go ahead and take a look here and calculate now the pH of a solution of hydrochloric acid of a concentration 1.0 times 10 to the negative 10th molar. Now, first thing I want to do is to recognize that I have a strong acid species here, that is HCl, and as such, this strong acid will undergo complete dissociation in solution into hydrogen ions and chloride ions, and therefore I am safe to assume that the hydrogen ion concentration from this acid is equivalent to the nominal molarity of the molecular HCl, that is a hydrogen ion concentration of 1.0 times 10 to the negative 10th. And therefore, with that hydrogen ion concentration, I might jump straight to finding the pH by taking the negative log of that concentration. A negative log of 1.0 times 10 to the negative 10th would yield a calculated value of the pH here of 10.00. And having made this calculation now, I should have some alarm bells going off in my head that this answer makes absolutely no sense whatsoever. How is it that I am dealing with a solution of a strong acid here, which is yielding a pH of 10, which is very much in the basic range of our pH values? And the thing I need to recognize here is that I've skipped over one of the important steps in terms of determining the pH of the solution, which was to determine all of the different species present in the solution that might produce hydrogen ions. In addition to hydrochloric acid being a species which generates hydrogen ions in this solution, we also have to remember that the autoionization process of water will also generate hydrogen ions as well. Now, I recognize that hydrochloric acid is a much, much stronger acid than water is, recognizing that its Ka value is very large in comparison to water's very small Ka of 1.0 times 10 to the negative 14th. But I also recognize that for the strong acid HCl, my concentration of this acid is so very small, that is 1.0 times 10 to the negative 10th molar, that it's going to be producing hydrogen ions which are essentially 1,000 times lower in concentration than the hydrogen ions produced via the autoionization process in pure water. Which means, therefore, even though hydrochloric acid itself is the stronger acid in this system, it is water which is going to be the dominant producer of hydrogen ions present in this solution due to the very low concentration of HCl. And as such, I can now determine that, in fact, the pH of the solution is instead really fundamentally determined by the production of hydrogen ions via water's autoionization process, which I know to be from previous discussions a pH of 7, given the hydrogen ion concentration of 1.0 times 10 to the negative 7th molar in a pure water solution. So long story short, even though this acid itself is present and added to this solution, it is at such a low concentration that it is essentially not important in comparison to water's contribution. And the long story short about this is to take away the idea that you need to consider all of the different species in solution that can generate hydrogen ions before you start simply just going through and making algorithmic calculations. So with that word of warning taken care of, let's now go ahead and move on to our next type of problem. All right, for this next slide, we're going to take a look at an idea which we discussed with you last year during your introduction to chemistry, but we want to kind of bring back and see in a slightly different light this year. We're going to be looking next at an idea we call the percent dissociation or the percent ionization of an acid. Recall from the process of the small k assumption when solving an ICE table that we, as part of that process, calculated the percent error in our calculation by dividing the x value, that is the thing we assumed was small in making our assumption, dividing that x value by the initial concentration of the initial species and multiplying that by 100 to express it as a percentage. Now, in previous ICE tables, this had really represented a percent error that we'd introduced into our calculations, but we want to look at this from a slightly different perspective now today with respect to those weak acids. In making that calculation, we are finding, again, essentially the x value, which recall is the concentration of those dissociated ions in solution at equilibrium. We're dividing that by the initial concentration of the molecular acid, HA, and multiplying that by 100 to express it as a percentage. What we're really finding, therefore, is the percentage of the initial acid, the molecular acid we started with, which has dissociated into its component ions. And as such, we would expect to see for a weak acid a very small value calculated for this percent dissociation, which really represents the idea that weak acids do not dissociate particularly effectively. That is, they have a very small percent ionization. In contrast, for a strong acid, where the strong acid completely dissociates into its component ions, we'd expect to find then a percent dissociation of 100%, where the dissociated ions are the same concentration as the nominal concentration of the molecular acid we started with. Now, we had approached that idea a little bit last year, but this year we're going to take it one step further and use a percent ionization as a tool for helping us to operate within an ICE table. So take a look with me now at example number 5, in which we're going to ask you to calculate the acid ionization constant Ka for lactic acid, that is the organic acid chemical formula HC3H5O3, if a 0.100 molar solution of lactic acid itself is 3.7% ionized. And as a starting point, we're going to go ahead and do the things that we already know how to do for these problems, which is to set up an equation showing the dissociation of that molecular acid into its component ions. That would be H positive and the lactate ion C3H5O31 negative. And down below that, we can now also set up an ICE table. plugging in the pertinent information they've given us, which is the initial concentration of 0.100 molar, and assuming initial concentrations of 0 for the dissociated ions in solution. From here, we'll go ahead and do the things we know how to do with an ice table. That is, we will define the changes in concentration in terms of X. For the molecular acid, that is going to go down in concentration by some amount, X moles per liter, giving us a plus X for the hydrogen ion change in concentration and a plus X for the lactate ions change in concentration. And from this point, we're now going to go ahead and skip forward to have a look at writing the Ka expression that governs this equilibrium. As always, the Ka value is the ratio of the products divided by the reactants, which in this case would be the concentration of hydrogen ion times the lactate ion, all divided by the concentration of the molecular lactic acid HC3H5O3. Now, let's pause for a moment here and take a look at the other piece of information which they've provided us in this problem. They have told us that the percent ionization of our lactic acid is 3.7%, which again means that 3.7% of the initial nominal concentration of lactic acid has undergone dissociation into its component ions, which really means, therefore, that the X value, when expressed as a percentage of the initial concentration, is going to yield us a value of 3.7%. And as such, I could write an expression now, that is, my X value from the ice table divided by the initial concentration of 0.100 molar times 100%, since again this is a percentage, will equal that percent ionization of 3.7%. And then I can just simply solve for my X value out of the expression I have just written right there. Solving for X in this expression yields an X value of 0.0037 molar. Now that I have an X value, I can simply solve the remainder of my ice table. As the concentration of the dissociated ions in solution at equilibrium are both equal to X, that would yield hydrogen ion concentration and a lactate ion concentration of 0.0037 molar for both of those. And finding my concentration of the molecular acid at equilibrium, I would take 0.100 minus X, which now gives me to the correct number of significant figures, 0.096 molar for my equilibrium concentration of lactic acid. Now that I know the equilibrium concentrations of all species, calculating the value of Kh for this expression is simply just a matter of plugging in those equilibrium concentrations to my Ka expression. And as I do so, we'll find here a Ka value of, in this case, hydrogen ions concentration of 0.0037 times the lactate ions concentration also of 0.0037, so I get a 0.0037 squared in my numerator, divided by the concentration of my lactic acid at equilibrium, which we calculated to be 0.096 molar. And making a calculation of that ratio, I get now a Ka value in this problem of 1.4 times 10 to the negative 4. Now that Ka value is a small value of Ka, which again correlates to an acid which we would expect to be a weak acid. And again, that correlates to the percent ionization, which we'd observed here, which was a low percent ionization. So all of those values kind of get to the same key idea, which is that lactic acid does not dissociate particularly effectively. So we've seen now we can calculate percent ionization, but we can also use that as a tool to kind of work our way backwards into the ice table and solve for X in a kind of unique way in this problem. So that's a good one. Let's take a look at our next slide. All right, for our next example problem, we're going to go ahead and have a look at another ice table problem. This is a kind of unique approach to a problem that's maybe different than what you've seen in the past, but the nice thing about these ice tables is all of these problems kind of start the same way. That is, you're going to start by doing all the things you know how to do. You know how to write a hydrolysis reaction or dissociation equation for an acid, you know how to set up an ice table, and you know how to write a K expression. So if you're faced with kind of a different approach to one of these problems that you've never seen before, my best advice is to just start by doing all those steps you know how to do first, and then kind of see how you can fit the puzzle pieces together to come up with the idea that you're looking for. So for our example problem here, we're given the pH of a 0.063 molar solution of hypobromous acid, that is HBRO, and that given pH is 4.95. And we're asked to calculate now the value of the acid ionization constant Ka of this species. So as I discussed, let's just go ahead and start by doing all the things we know how to do. First of all, by writing a equilibrium equation governing the dissociation of this acid. I'm going to start off with the species HBRO and show it dissociating into its component hydrogen ion and the hypobromite ion BRO1 negative. Now that I've written this dissociation equation, I'm now going to go ahead and set up an ice table and plug in the information which is given to me. My initial concentration of the molecular acid was labeled as 0.063 molar, and I'm going to go ahead and assume initial concentrations of both hydrogen ion and the hypobromite ion of 0, as we have seen in the past. I can now define my changes in concentration of a minus X for the molecular acid, and then plus X for both of the dissociated ions respectively. And at that point, I can define my equilibrium concentrations of 0.063 minus X, and then X and X for both of the dissociated ions. So I've set up my ice table as I've seen how to do, and my next step is to write my K expression. The Ka, which governs the dissociation of this acid, is going to be equal to the concentration of hydrogen ion times the hypobromite ion, all divided by the concentration of the molecular acid HBRO. So I've kind of gone through now all the steps for things I know how to do, and now let's take a look at the other piece of information which was provided to me in this problem. That is, the pH of my solution has been given as 4.95. With a given value of pH, I recognize that I can easily calculate the hydrogen ion concentration in this solution by using my pH square. So I'm going to go ahead and do that next. My hydrogen ion concentration is 10 to the minus pH power, which in this case would be 10 to the minus 4.95, which when I plug this into my calculator, it gives me a value of 1.122 times 10 to the negative fifth, which I'm going to again round to two significant figures, given my two sig figs from the pH, remembering that the value before the decimal place in my pH is not one of the significant figures for this calculation. So again, I get a pH of 4.95, yielding a hydrogen ion concentration of 1.1 times 10 to the negative fifth molar. And having now defined that hydrogen ion concentration, I can look back to my ice table and recognize that the hydrogen ion concentration in this solution is the value of X in my ice table. And with that given value, I can now simply solve this ice table very easily without having to go through and make any assumptions. So let's go ahead and then plug in values of 1.1 times 10 to the negative fifth molar for X, both for the hydrogen ion concentration and for the hypobromite concentration. And then my hypobromous acid concentration is 0.063 minus X, which within our sig figs measured is still going to be a value of 0.063. But again, I'm going to carry all those extra places through on my calculations so as not to introduce compounded rounding errors when I go through to make my final calculation of the value of Ka. And now that I've got the equilibrium concentrations of all species, I can simply go ahead and plug into my Ka expression and solve. So my Ka value is going to be equal to, therefore, 1.1 times 10 to the negative fifth, which gets squared, all divided by my initial concentration of 0.063 minus the X value of 1.1 times 10 to the negative fifth. And a quick calculation there finds for me here a Ka value of 2.0 times 10 to the negative ninth for the Ka of this very weak acid. So again, we've never seen this type of problem before, but by manipulation of our understanding of the ice table and just kind of doing the steps that I know how to do, I can find an easy pathway here to a solution. All right, and with our last slide in this lecture, we come to the grand finale problem for acid-base calculations. That is that we're going to ask you to calculate here now the concentrations of all species present in a mixture of two different weak acids. In this case, that is a 1.00 molar solution of HCN, hydrocyanic acid, and a 5.00 molar solution of HNO2. Now, this is kind of a big problem, and my best hint for success is number one, to keep yourself organized, and number two, to focus on the chemistry of the system rather than getting kind of bogged down in the calculation details. So, with a goal in mind of keeping ourselves organized, let's go ahead and start just by listing all of the species that's going to be necessary for us to find concentrations of in our solution, since again the question asked me to find both the pH as well as the equilibrium concentrations of all species present. So starting off, if I am looking at the species present, number one, I know that I've got the molecular acids. Those are HCN, hydrocyanic acid, as well as nitrous acid, HNO2. Additionally, I'm familiar with the idea that each of these acids are going to dissociate into their component ions, which means we're definitely going to have the hydrogen ion present, as well as the cyanide ion and the nitrite ion, those again being the ions formed from the dissociations of our acids. And then last but not least, let's not always forget here that in any aqueous solution, in addition to having hydrogen ions present, there also will be the presence of the hydroxide ion as well. So I've identified now all of the things I'm going to have to find. Now we can go about starting our process. As a starting point, let's go ahead and have a look over here. I've listed for you in this table the major species in solution as well as the respective Kas of the three species. Those are number one, hydrocyanic acid, HCN, whose Ka is 6.2 times 10 to the negative 10th. Number two, nitrous acid, HNO2, whose Ka value is 4.0 times 10 to the negative 4th. And then also always remembering that we have another species present that can act as a generator of hydrogen ions in solution, that is water, the solvent itself, whose Ka value is that of Kw, the autoionization constant, of 1.0 times 10 to the negative 14th. So looking at those three Ka values, the first thing that I notice is that the species HNO2, that species is orders of magnitude stronger as an acid than either water or hydrocyanic acid. And as such, the nitrous acid HNO2 is going to act as the primary contributor of hydrogen ions in my solution. Because that nitrous acid is such a stronger acid in comparison to any of the other species present, I'm going to focus my start of this problem by dealing simply with the equilibrium involving the dissociation of nitrous acid into its component ions of the hydrogen ion and the nitrite ion, and work our way from there. So let's just start off by doing the things we already know how to do, which are to, now that we've identified the major contributor of hydrogen ions to the solution, write a dissociation equation showing the production of that hydrogen from our nitrous acid. So I'm going to go ahead and write here, HNO2 dissociates into the component ions of a hydrogen ion, H positive, and a nitrite ion, NO2, 1 negative. Now that I have my dissociation equation, I'm going to go ahead and set up my ice table here. My initial concentration of the nitrous acid was given as 5.00 molar, and I'll insert values of 0 for both the hydrogen ion and the nitrite ion under the initial states. From here, my change in concentration is easily defined as a minus x for the molecular acid, and then a plus x and plus x for the hydrogen ion and the nitrite ion respectively. And that will leave me now with equilibrium concentrations of 5 minus x molar for the nitrous acid, and then x and x for both of the dissociated ions. So I've got an ice table set up. I can now go ahead and do my next step that I'm familiar with, which is to write the K expression that governs this equilibrium. This is a Ka, an acid ionization constant, which is going to be defined as the products over reactants, that is the concentration of H positive, times NO2, 1 negative, divided by the concentration of HNO2. And we've seen a lot of these so far. We know the next step is to now plug in my equilibrium concentrations defined in terms of x into that Ka expression. So from here, I've got a Ka value of my nitrous acid of 4.0 times 10 to the negative 4. That will be equal to now, at equilibrium, x squared divided by 5.00 minus x. And recognizing again, because I have a small value of k, that implies a small k assumption is appropriate here. I'm going to go ahead and assume that the value of x is very small compared to our initial molarity of 5 molar of that molecular acid. And as I do so, this simplifies down now my expression to the Ka value of 4.0 times 10 to the negative 4 is now equal to x squared divided by 5. Real quick solving here, multiplying by 5 and taking the square root of both sides gives me an x value in this problem of 0.045 molar. And as I did make an assumption, I needed to check my assumption to make sure it was a valid one. Again, we'll divide our x value by the initial concentration, so 0.045 divided by the initial concentration of 5.00 molar times 100% gives me now a percent error introduced by that assumption of 0.089%. Well within our 5% range we consider to be acceptable. And also, I recognize that this makes logical sense because, again, I had a weak acid. This is a small percent ionization we've just calculated here. All right, so we've solved the first ice table, and that means we can now go ahead and think about what we currently know. So again, we've done the calculations, now let's do the thinking. In terms of our x value, that x value is equal to the concentration of both hydrogen ion in solution and the nitrite ion NO2 negative. So I'm going to go ahead and fill in the nitrite ion's concentration of 0.045 molar, and I can now also easily calculate the concentration of the nitrous acid at equilibrium, which is 5.00 minus my x value of 0.045 molar, and that gets me now a value of, what is that, 4.95 molar with significant figures for the equilibrium concentration of HNO2. Now, I know what you're thinking right now. We just found the hydrogen ion concentration, but there's another species, or in fact, two other species that could possibly produce hydrogen ions in our solution. That is the hydrocyanic acid, HCN, as well as water itself. But remember, as we looked back to our initial discussion there of the Ka values, that the hydrocyanic acid is orders of magnitude weaker in its acidity than the nitrous acid. And as such, yeah, it's going to be making some more hydrogen ions, but they're probably going to be negligible in comparison to the concentration of hydrogen ions formed from the HNO2. And as such, I'm just going to go ahead and record now my hydrogen ion concentration in this solution as 0.045 molar, recognizing that yes, some more will come from the next dissociation of our next acid, but it's going to be so small that it's really not going to matter. Now that I know the hydrogen ion concentration, I'm also able to calculate the hydroxide concentration by using my pH square and really the value of Kw as my calculation tool. My Kw is equal to the concentration of hydrogen ion times the concentration of hydroxide ion, which when rearranged gives me now a concentration of hydroxide ion equal to Kw divided by the concentration of H positive. That would be equal to 1.0 times 10 to the 14th divided by my hydrogen ion concentration of 0.045, which comes out as a value of 2.2 times 10 to the negative 13th molar. So I can now fill in my concentration of hydroxide ion as well, and we're in pretty good shape moving forward. So we've now dealt with our initial equilibrium system. Now let's go ahead and move on to the second equilibrium involving our second acid, that is the hydrocyanic acid, HCN. I'm going to go ahead and do the same things that I've done on the previous step, which is I'm going to write my dissociation equation and then move on from there to solve an ice table. My HCN will be shown dissociating now into hydrogen ions and cyanide ions, Cn negative. Setting up the ice table and plugging in my initial concentration of HCN of 1.00 molar. Now take a quick moment and please be very careful here. The initial hydrogen ion concentration is no longer assumed to be a value of essentially 0, but now a value of 0.045 molar, that is the hydrogen ion concentration from our previous dissociation of the nitrous acid, becomes my concentration that I'm going to start my ice table with here now for the second step. And then again, the cyanide ion concentration will be a value of 0 molar. Defining my changes in concentration, again, this equilibrium must be shifting to the right since I've got a 0 for the cyanide ion under my initial concentration. So I'm going to define concentration changes of minus x for the HCN, and then plus x and plus x for the hydrogen ion and the cyanide ion, yielding me equilibrium concentrations of 1.00 minus x for HCN, 0.045 plus x for H positive, and x for the cyanide ion Cn negative. And now that we've got the ice table set up, we're off to go ahead and solve the way we know how. That is, we'll write our Ka expression. Our Ka expression is the concentration of hydrogen ion times the cyanide ion divided by the concentration of the molecular acid HCN. And now substituting in our equilibrium concentrations defined in terms of x into that ice table gives me a value now of the Ka for HCN of 6.2 times 10 to the negative 10th, being equal to the concentration of H positive, which is 0.045 plus x, times the concentration of Cn negative, which was x, divided by my equilibrium concentration of HCN, which is 1.00 minus x. And again, I'm going to simplify this by making our small k assumption again. I have an even smaller value of k, which means this assumption is probably even more valid than it was before. We'll go ahead and plug in here 6.2 times 10 to the negative 10th is now equal to, upon assuming that X is very small compared to the initial molarity now of 0.045. That would give me now an expression of X times 0.045 plus a tiny number is essentially 0.045, divided by 1 minus a tiny number, which is essentially just 1. And solving here easily by dividing both sides by 0.045 yields me now an X value of 1.4 times 10 to the negative 8th molar. And just to keep things tidy here and dot all our I's and cross our T's, we'll check our assumption here. Our X value of 1.4 times 10 to the negative 8th divided by that initial concentration of 0.045 times 100% gives me now a percent error introduced of 3.1 times 10 to the negative 5th percent, a tiny, tiny, tiny introduced error, which really again correlates to the idea that this acid is not dissociating particularly effectively, not surprisingly, given that, number one, it was a very weak acid to begin with, and also, number two, that we had increased the concentration of hydrogen ion, which should push that equilibrium even further to the left for this second dissociation. So I now have an X value, which is, as you see from my ICE table, equal to the equilibrium concentration of the cyanide ion. So I can fill out that cyanide ion's concentration is 1.4 times 10 to the negative 8th molar, and hydrogen ion's concentration is 0.045 plus my X value, which clearly we can see is not going to have a meaningful change in concentration from the initial concentration of 0.045, given how very, very small that increase in concentration was. So that one's going to remain at 0.045 molar. And the HCN's concentration of 1 minus X is essentially unchanged at 1.00 molar within the sig figs which we can measure. So I now have the concentrations of all species present in my system. All that remains to be done for completion here is to find the pH of my solution. The hydrogen ion concentration we had previously calculated, it was 0.045 molar. Taking the negative log base 10 of that value to find my pH yields now for me a pH of 1.35, a very acidic solution overall, making sense given that I have two relatively concentrated acids here in our system. So, long story short, lots of organization, but really just simply applying the ideas we've seen in the past and making sure you take the time to slow yourself down and think about the primary contributor of hydrogen ions to your solution and what that really means in terms of the equilibrium positions of the system for both acids present. That's that for our lecture here. Thank you for listening.